So guys, I'm going to suggest though that the way to start this is by sort of revisiting what we've said up until now about PES. Because my fear is that we got here so hurriedly that while we're here, we're not really here. Okay? So this is what we've said relative to PES. We've said that PES is the process of figuring out the electron structure of an atom by bombarding it with energy. And we hit it with energy in what form? The form of light, the form of photons. It's not necessarily visible light. Some of the most interesting PES is actually done with X-ray photons, but that doesn't really matter. But the idea then, because I'm going to close this door, the idea then is that we bombard these atoms with energy in the form of light, photons. And guys, what that energy does, it excites electrons. And now the excitation of those electrons does two things to the electron. First of all, it breaks it free. And then if there's extra energy around, what then happens to the electron? It accelerates, right? And so the math of that is represented here on the board. That the left-hand side of the equation represents the way that we can calculate the amount of energy going in the form of a photon. Then the electron binding energy is representative of what? The energy needed to do what? Bust the electron free. And guys, up until now, you wouldn't have called that electron binding energy. You would have called it ionization energy, right? And then guys, any energy that's left over. So this is energy in, this is energy used up. Any additional energy that is present from the incoming photon then goes to accelerate the electron out of the nucleus, or out of the orbit, if you will, of the atom. Now guys, understand that the way that we do this is sort of backwards to the way that we presented it. See, this we know. We know the energy of the photon. How do we know? Because we're the ones that are picking the light source. And typically we use lasers. And lasers, I don't know if you know this, guys, lasers are what are called monochromatic light. Light of one wavelength. As a matter of fact, it's printed on all of these things. So, where does it say it? Oh, right here. So guys, the light of this laser has a wavelength of 532 nanometers. So when we look at this green light, all we are seeing is 532 nanometer light. And guys, understand that doesn't exist anywhere in nature. There's no such thing as monochromatic light. It's only man-made. When we see any other light source, it's actually a blending of many different energies. But guys, when we do laser light, this is caused by exciting and allowing one electron fall to take place. And this is monochromatic, in this case, 532 nanometer light. We can convert that to a frequency. We can convert that to an energy by doing that. So guys, the bottom line is we know this. We know with certainty the energy that's going in. What we do then is we figure out this. Do you remember how? How do we figure out the kinetic energy of the electron? Exactly. And so let me bring in the rest of the slide, and it looks like this. And over here we have our electron detector. And we know this. We know the distance between the atom and the detector. And so, guys, we can then figure out the kinetic energy because, oh, that's not new. That's velocity. We know the kinetic energy because that's 1/2 mv squared. We know the mass of the electron. We can look that up in a book. we can figure out the velocity of the electron by simply knowing the distance between the atom and the detector and then timing how long it takes for that electron to travel this distance. And velocity is distance divided by time, which gives us the V in kinetic energy, and we can figure that out. You guys good to there? Okay, go ahead. Correct, yeah. So, well, understand let me say it this way. There are multiple variables that represent three separate things. So this, which is two variables, sort of, is how we know the energy of the photons. We know the frequency, and Planck's constant is a constant, okay? Then here, kinetic energy is one thing, but it's actually 1/2 mv squared. We know the mass of the escaping electrons. We call them photoelectrons. We know the velocity of the photoelectrons. We know the mass. We can look up the mass of electrons. We can figure out the velocity by knowing this distance and then timing how long it takes the electron to get there. And that then allows us to calculate kinetic energy. Then this electron binding energy is just one thing. And really, the equation to calculate electron binding energy is equal to the energy of the photon minus the kinetic energy of the escaping electron. If you just reformulate this like that, that's how you figure out the electron binding energy, is you know the energy of this, you subtract the kinetic energy of the escaping electron. The difference between those two must be the energy with which the electron was held, and we call that electron binding energy. Okay, just a minute, Brandon. And so we talked about this sort of like fictitious example that said, what if we put in 20 electron volts, and what if the kinetic energy coming out, thank you, was 6.4 electron volts, and by subtracting those, the difference is not that. The difference is 13.6 electron volts, which happens to be the energy or the electron binding energy of the first energy level. Is that all coming back to you? That's kind of where we stopped on Mondays. So let's do questions. Correct. And so here's the trick. And this is sort of the place where things got confusing on Monday, and we gave up and said we need to talk more Wednesday. Because you guys got concerned about this idea of how many electrons are coming out. So the idea is this. What does this look like? Well, guys, what we would have is we would have a chamber. Picture the tubes that we excited when we did the spectra lab. It's literally a glass chamber full of hydrogen gas. And you pulse. It's not like putting it in the voltage source. You take that chamber of hydrogen gas and you basically take an X-ray of it. You pulse it with X-ray energy or light or whatever you choose to do, but you pulse it and you're hitting that thing with millions of photons. And those photons interact with these electrons in hydrogen, and these electrons eject down to the detector. And so guys, the trick is this detector, so you understand, this is our electron detector. The detector detects two things. It detects time, so it tells you how long it took the electrons to get there, and it also detects abundance, or the number of electrons that hit. So what you would end up with then is you would end up with this detector saying, I caught this many electrons in this amount of time. But if this is a hydrogen atom that only has one electron in the 1s sublevel, all of these electrons would come out simultaneously. They would all excite simultaneously, and so this electron detector would go, holy buckets, I just got hit with a pant load of electrons, and they all hit me at exactly the same time, meaning they're all coming from exactly the same place. Does that make sense? What's that? You don't have to remedy it, you have to interpret it. What? Sure it will, because all we need to know is the time. We know, so the only data that we need from the electron detector is time. Because if we know time, we can measure distance. Time and distance give us velocity in 1/2, sorry, I keep doing that, 1/2 mv squared, which allows us to calculate this. We know this because we're the ones that put in the light. By subtracting, we can figure out electron binding energy.
Yes, electron binding energy, kinetic energy equals 1/2 mv squared.
Yep.
We know the mass
Yep.
of
An electron,
we have the time.
the detector tells us the time with a ruler. Literally. So what does this thing look like? And quite literally, there is a gas-filled tube. Well, here, I'll draw it the way we're seeing it. There's a gas-filled tube that has, in this case, our hydrogen atoms inside of it. And then we've got a fluoroscope that's got some coil in it that generates either light or X-rays. So there's our incoming source. And then over here, it kind of looks like a solar cell. It actually is a solar cell, sort of. And there's a thing that looks like a solar cell over here that's hooked up to a computer. And that thing, just as these electrons come out, detects them. And you can physically measure that distance. Just measure the, yep, that's all you need. Exactly. So we measure the distance. This thing tells us the time. That's 1/2 mv squared. We know the amount of energy that went in because we picked the wavelength of the energy we're putting in. So we know the energy of this because that's h nu. We know the energy of the kinetic energy of the electron coming out because we know the mass. We can figure out velocity because that's distance divided by time. Subtract the two. That gives us the electron binding energy, which tells us the ring that it's coming out of. Do you get the idea, guys? You okay? And so now it's just time out. You gotta understand the way the thing works before you can interpret its data. So do you understand the way the thing works? Questions that you need to resolve. Go ahead, Becca.
So are you saying that no matter how many photons you take the hydrogen, you have the whole hydrogen atoms?
Yeah. No, you'd have to hit it with a mole of photons, and each one of those photons would have to hit an atom. And understand, this is not completely efficient. A lot of the light goes through. What I am telling you is it doesn't matter how many come out. The reason that it doesn't matter is all that we're trying to do is measure time. And they'll all come out simultaneously, and it doesn't matter if one comes out or 100 or 1,000 or a mole, they'll all come out at the same time because they were pulsed in the same instant, and they will all excite similarly if it's a hydrogen atom. And so because in hydrogen, they are all coming from the same place, they'll all come out and hit that detector at the same time. Exactly, and yes, precisely. So guys, maybe the big idea here is don't get caught up in how many. It doesn't matter. What we care about is the time, because time leads us to kinetic energy that leads us to the subtraction. Okay, but guys, as I say that, understand that in a minute, you're going to find out that amount does matter, but it's only relative amounts. And I'll show you what I mean in a minute when we look at atoms like lithium. Go ahead. We've only talked about it with hydrogen. We're about to talk about all the other elements. Okay. So guys, are y'all caught up with me? You guys okay? Okay. So guys, what then does the data from this look like? It's a valid question. And guys, this is what you've got to know, but I'm realizing I need to, just a second. Do you remember when I told you about the fight that broke out between, and they couldn't even agree on whether the axis goes from high to low or low to high? I don't remember now. Okay, I just had to remind myself. It goes from low to high. So guys, what does the data from this look like? Well, let me show you. So back here, this is what the data from this looks like. When you get to university and you start doing PES, again, I never did in college, but some of you may. What these things do, what these PES machines do, is they actually spit out their data as graphs. And guys, what happens is the computer that's analyzing the data, and let's go back through it one more time, the computer that's analyzing the data does a lot of the math for you. So we understand that Planck's constant is a constant, and you can input the frequency. And actually, a lot of these PES machines have really interesting fluoroscopes where you can just turn a knob and say, I want an X-ray photon, I want a violet photon, I want an infrared photon. You can just, and then it just changes the makeup of the of the coil that creates different photons. It's pretty cool. So guys, the PES machine will actually keep track of this and do the math for you. You can input the frequency of the photon you want, it'll make it for you, and it knows Planck's constant. Now guys, it also does this for you. It knows the mass of electrons, and it knows the velocity because it's actually measuring the distance. It's a set distance, as we now understand. It measures time, and it does this math for you, plugs everything in, and it kicks out for you the electron binding energy. So what does it look like? But do you understand what I'm saying? It does all the background math, and the information it gives you is the electron binding energy. Okay? What it looks like then is this. The data that comes out of a PES machine comes out as a graph. And the way that it goes is the graph is abundance of electrons on the y-axis. And it's a dimensionless number. These are relative abundances. And then on the y-axis, or the x-axis, it gives you electron binding energy from some maximum down to 0. Okay? And so, guys, if we pulsed hydrogen, this is what the PES graph of a hydrogen atom would look like. It would be nothing, and then it would be a peak, and then it would be a nothing. And where would that peak lie? At 13.6 electron volts. You get it? So guys, that is what the graph, the PES representation of a hydrogen atom looks like. It tells you that all the electrons in a hydrogen atom have an electron binding energy of 13.6 electron volts, and that's what hydrogen would look like. You get the idea? Okay, now let's try this. I don't think I can save this, but I'd like to. Well, burn that into your memory. You ready? Okay. Now, guys, let's do this. Let's go back to our picture and let's remember what we talked about last time, and let's make this helium. So, guys, in order to make this helium, this is now going to be 2 protons, right? And this is now going to be 2 electrons. But, guys, what happens to the effective nuclear charge? What happens to the Coulombic attraction that these 2 electrons see? Relative to hydrogen, will that attraction be greater or smaller? Greater. And so functionally, what will happen to these two electrons? They will move towards the nucleus because they are both seeing a greater Coulombic attraction, which means they are more attracted to the nucleus. So guys, in helium, remember we're still in the 1s sublevel, right? But guys, in helium, remember in hydrogen, this was 13.6 electron volts of binding energy. Guys, what would it be in helium, greater or less? It would be greater. I frankly don't remember what it is. We can look it up, but it's greater. So the question then becomes this. I'll be interested to see if this works. Let me go back to white screen, and then let's see. Oh, cool. Okay, so this is hydrogen, right? Here's the question. If we then did, and I'm going to superimpose one over the other, if we now do a PES study on helium, how would it look different? Go ahead. More towards the zero? Yeah, this is electron binding energy. Would it move left or right? Do you understand that, guys? Do you understand why? Okay, so the idea, let me see if I can do this. And I love that you're saying no, because here. Good. So the idea is this. So guys, helium has a stronger nucleus because it's got 2 protons, right? That pulls these electrons tighter together, which means it's going to be harder to get them away. So they have a stronger electron binding energy. And guys, understand, did that make sense? So understand that when we go over to this graph, this is a lot of electron binding energy, and this is no electron binding energy, and the electrons in helium are more tightly bound, and more tightly bound is in this direction. Do you get that? Okay. But guys, how else will the graph be different? Twice as tall. Guys, it actually looks like this. The curve will look like that. What does it tell you that the peak is twice as tall? There's twice as many electrons. It's helium and not hydrogen. And again, it doesn't matter how many, these are relative to one another. Just a moment. And then guys, notice that this is shifted to the left, and we're going to say something important, don't miss this. This is shifted to the left, showing us that these electrons are more tightly bound. So guys, let me do this and see if this makes sense. I don't know, let's go black. So if we could bring this down, that was too much for it to handle. And if we bring this down, what does this distance and this distance actually represent? The radius of the atom. Do you get it? Guys, this is the nucleus. And the tighter bound an electron is, the closer it is to the nucleus. So, when you look at these electron PES graphs, understand that the location of the peaks is actually analogous to the radius. You can't directly calculate one from the other, but it is relative, because the more tightly bound electrons are, the closer they are to the nucleus. And guys, that's what brought on the fist fight during that conference that I was at, was if you were to flip this and make this 0 and make this maximum binding energy, then it's no longer analogous to radius, because now the closer you are to the origin of the graph, the less tightly held the electrons are, and everything goes ski-wampus in your brain. So finally, all of us stupid high school teachers that aren't smart enough, they would say, to understand what college people think they understand, finally said, listen, put maximum on the left and 0 on the right, because that's going to make sense to our kids and to us. And they decided, okay, we'll do it that way. Guys, it doesn't have to be that way. You could flip and the data is still the same, but it's not as visual anymore. So understand, if the nucleus is over here at the origin, then this distance is analogous to the radius of the atom. Do you get it? Okay, so go ahead, Jake, but keep us on topic.
So because the shapes are triangles, was there any variance?
Yeah. Well, so so interesting. So, yeah. So why is it that it just doesn't do this, right? And I don't understand all of it, but I did have explained to me that part of the reason. I wonder if I can go back this far. Yes. Wow, that's cool. Part of the reason is because if you excite an electron in an atom that's right there, it is actually a little bit closer to the detector than if you excited an atom that's over there. That's just unavoidable because all of the atoms are not in the same plane. Consequently, they're not exactly the same distance from the detector, which does create a little bit of a range of values for velocity because they are traveling slightly different distances, and therefore it gives you a range in values within your electron binding energies because you're subtracting slightly different numbers. I'm sure that there's other reasons as well, but that was the reason that was given to us. So, yeah, but I agree with you. I expected these to be real tight peaks, and they're not. Go ahead, Joel.
Wouldn't it also be because the electron isn't always exactly there?
Absolutely, yeah. That's an interesting point that they didn't even mention, but that has to be true, right? That if these electrons are probabilities, and if we're measuring such short distances anyway, absolutely, the specific location of that electron when it excites would matter as well. That's a great point. You guys with me? All right, so now guys, check this out. Oh, mama, how am I going to do this? No, I'm going the wrong way. Okay, so now we're back to our graph. Okay, so we're going to clean this up like this. Now, guys, let's do this. Let's now take this and let's do lithium. So lithium has got 3 protons. It's got 2 electrons in the 1s, and then it's got 1 electron in the 2s. Yeah? Okay, here's what I want you to do. Go over, this is going to be easier from my computer. Do you understand lithium? So guys, do this. Go to this. Are you drawing this in your notes? If you're drawing this in your notes, do it in your notes. If not, do it mentally. Guys, given what we did for hydrogen and helium, what will lithium look like? Draw lithium. And guys, if it's helpful for you, I can do this. 3 protons, 2 electrons, 1 electron. Draw lithium. Do you understand now why I decided to take this into a second day? Yeah. Did you get it? So guys, allow me to take a swing at this. Here's the thing that I love is it's fun to hear you guys talk about the way you're thinking about this. Allow me to think out loud as you were thinking out loud. So we understand that we've got 3 electrons, right? But if we ignore this third electron, let me just sort of cover it with my hand, what do we kind of have with just these 2 electrons? That's helium, right? But now, guys, let's just focus then on these 2 electrons, because those are, if you will, the same electrons in helium. But guys, relative to helium, will these electrons be bound more tightly, less tightly, or the same? More tightly. Why? We've got 3 protons. So what that will do is it will shift this 2 electron peak even further to the left. So now let's talk about the third electron. Guys, we've only got 1 electron in the 2s energy, the 2s sublevel. But what about the energy with which that electron is bound? They're good. They're shielding. And that shielding causes this electron to be less tightly bound. So what we would expect then is 1 electron that is less tightly bound. So it's less tightly bound, so its peak will be to the right, and there's only 1, so its peak will be like this. Okay, so let's do it. Guys, hold on. I'm going to run out of colors, but oh my, we're going violet. So guys, now what do we do if we look at element number 4, which is beryllium? Well, now we've got 4 protons. Now we've got 4 electrons. So guys, what will beryllium look like? Well, we're going to have another 2 electron peak. Where will it be relative to lithium? Even further to the left. Now we're going to have another peak. How big will it be? It'll be a 2 electron peak. And where will it be relative to lithium's 1 electron peak? Further to the left, and it'll look like that. Yeah? Because of the 4th proton in the nucleus. So the 3 electron nucleus of lithium exerts an electron on here, but you're the one that said shielding, right? But now in beryllium with 4 protons, these 2 electrons still are shielded, but because the nucleus is stronger, these are more tightly bound, moving that peak to the left. Yeah, Tracy. To be honest with you, I don't even know if you can do that. Hold on, have we ever done that? We've identified these energy levels by energy. Have we ever identified them by actual radius? I know it can be done, but it's not something you need to do. What you need to be able to do is look at these and understand what these relative positions represent. But you would also have to be able to do something like this. If you had this, what is that? Well, you've got 2 electrons that are tightly bound, 2 electrons that are less tightly bound, and then 1 electron maybe that is even less bound than that. That would be boron. And then, well, it gets, actually, you know what, it gets even, we'd have to do this. So it would be, and that might be boron, and then shifting them all over. Well, let's just go really crazy and let's do neon. Neon might look like that, right? Because you'd have 2 electrons really tightly bound, the 1s, 2 electrons fairly tightly bound, the 2s, and then 6 electrons. So this should be 6 times, well, 3 times taller because that represents 2. And that would be in the 2p. And actually, probably it should be a little bit closer because the energy difference between, it should probably be like this. Like so. Because the energy difference between the 1s and the 2s and the 2p is actually quite small. But that would be neon. So, what do y'all think? Questions? Go ahead, Becca. I don't know. Where do you want me to go?
The one where we have the 3 atoms.
That?
Yeah.
Okay.
So, how would you know that? So I understand you have 2 electrons and then 2s.
Which one are you looking at one in particular?
Yes.
Pick a color.
Okay. So if you have lithium.
Which one was lithium green? Okay, go. I'm looking at green.
And then versus beryllium, which has 2.
Which one is beryllium? Violet. Okay, green versus violet. Keep
So I
going.
understand that having 2 electrons with the 2s would make it closer to the nucleus and have 1 electron. But how do you know comparing that to hydrogen, which is blue?
Right, yeah, how do you know that relative position? And relative to hydrogen, it's easy because hydrogen has no shielding. So it's full on just attraction. There's no shielding. But beyond that, they're not asking you to make sense of that. But you would need to be able to look at something kind of like we did here and make sense of what possibly that could be, but you don't have to be all caught up in the relative positioning relative to other elements. Other than, like you would maybe need to be able to compare lithium green to beryllium violet, but the thing that you need to understand is there's a shifting here and a shifting here and a 2 electron peak there, but tracking that all the way back like to hydrogen you don't need to worry about. Yeah, go ahead.
So shielding is because of the repulsion.
Shielding, I mean, the term shielding is actually very descriptive. When we talk about shielding, what we're saying is these electrons in here. And guys, I don't know if I've ever shared this term with you. Feel free to use this on the test and the AP test. These are what are called core electrons. So given what we have talked about, core electrons are the electrons that are not valence, okay? And so literally what happens is these core electrons shield the valence electrons from the nucleus. They literally act as a barrier between the nucleus and the valence electrons. And as a result, those valence electrons don't see the full attractive force of the nucleus. We say they are shielded from the nucleus, and that makes that electron binding energy, that attachment, weaker. Does that make sense? Well, kind of think about it like, I mean, this isn't great, but sort of. I mean, oh, those are too strong. But if you've got 2 magnets, like say that these are north to south like this, go ahead and hold that for me. So, and I mean, imagine, right, they're so far away, this really isn't working. But then if I put another magnet in between now, that magnet is actually less attracted to this magnet because this magnet is interfering. Does that make sense? That's literally what's going on here because this magnet's attracted, so's that one. But when this magnet gets in between, it interferes and that magnet would actually be less attracted. That would be really cool to actually try. Like if you were to put little spring scales on those and get stronger magnets, you would actually, because if this could like stretch it in that direction, when you put this here, you'd see less stretch. I should try that. That's cool. All right. Did I show you guys the magnets that I bought? You could do it with these. Guys, these magnets scare the crap out of me. Like, check this out. Ouch. Oh. Ow. Oh, crap. Damn it. Yeah, that hurt. Like, it'll go through my calf. Okay, now I'm scared. Ow! Okay, I'm not doing that anymore. And I can't get them apart. I'm just going to leave these right here. Ow. Good night. That really hurt. We're going to leave those there. So, guys, bottom line is this. Are we done here? Are we good? Okay, so allow me to offer this to you, not as something that I'm going to provide you the opportunity to write down, but if you would like a summary of everything that we just talked about, this is it. We're not even going to read over it, but understand that if you want something to come back to as you're thinking about preparing for the test, this is a good overview. Now, guys, we could spend time and we could draw these sorts of graphs, which we frankly have already done. But guys, this is what I'm going to encourage you to do relative to the homework. We are actually going to grade this next time as homework because it's good preparation. Because I want you to try this. Grab a blank sheet of paper and draw the PES spectra of hydrogen through neon, the first 10 elements. But guys, draw them on the same graph. I really can't get these apart. Yeah, like my arm. Yeah, it really got me. But guys, that's where we're going to wrap up PES. So